So let's say when you integrate, so actually just write integral represents net change. Okay, so for us, sometimes that represents net distance that's traveled, because a lot of times we talk about velocity as what we integrate, and then the accumulation of the distance traveled is really the net distance. So here's a really, really basic example. If I travel 60 miles per hour, I'll sketch the curve over here. If I talked to you guys about traveling 60 miles per hour. Let's say this is V of t, and you guys are traveling 60 miles per hour towards UCLA. And after an hour, no traffic, you guys get there. So your distance here after 1 hour that you've traveled is 60. So this is 60 miles per hour. Okay, so it's positive 60 is your distance. And let's say that you head home after that. So when you head home after that, you're going backwards this time. So let's say, so there's a 1 right there. Let's say you go negative 60 miles per hour. Okay, and again, velocity has direction to it. So technically, if we're going backwards to back home, we're traveling at negative 60 miles per hour, no traffic. And the net distance here is negative 60, the net area. So if you guys think about integrating from 0 to 2, where 0 to 1 was you going forwards to UCLA, and then from 1 to 2, you're heading back home at negative 60 miles per hour, then your net distance, or what you've traveled over that entire time. So if I write this as an integral, the integral of that velocity function I just drew over there, dt, because this is your x value, your independent variable is t, from 0 to 2 happens to be 0. And that idea is really displacement, right? So if you guys are traveling 60 miles there and then 60 miles back, how much has your distance changed? Your net distance is 0. You're back home. Okay, so that's the idea behind what the integral represents. And so there's this whole idea behind, like, what's the difference between net distance and total distance, and how do we go about setting up our integrals for that? So over here, I'll just have you guys fill in. If if v of t gives the velocity of a particle, its antiderivative s of t its antiderivative is s of t, and so we have an accumulation of distance traveled. And so let's look at one problem that I want us to be able to figure out. Oh, actually, it's written right here. The example is right here. A particle moves along a line such that its velocity is given by this function. Time is measured in seconds and distance in meters. We want to find the total distance traveled by the particle, but I also want to discuss what the net distance is. Okay, so with net distance, it's really nice. I don't have to look at the graph at all. I just go, okay, well, I know the time is from 1 to 4. I know an integral represents the net distance. So if I take the integral of that function, t squared minus t minus 6, from 1 to 4, and I apply my knowledge of FTC, and just for a moment, let me scroll back up to here. Remember that FTC, Fundamental Theorem of Calculus, allows you guys to take the integral, find the antiderivative. If little f is your integrand, capital F represents your antiderivative. You plug in your upper limit of integration and then minus out your lower limit of integration. So here we're not really estimating the integral. We can find the actual antiderivative, so we're going to go ahead and do that. So if I find the actual antiderivative of this to find the net distance, it's t cubed over 3 minus t squared over 2. So again, increment the exponent by 1 and then times by the reciprocal of the exponent. So plus 1 on the 2 is 3 times by 1/3, plus 1 on 1 is 2 times by 1/2, and then minus 6t. And the way that you guys would plug it in is you would plug in the 4 first, and then you subtract out the 1. So I'm going to write out those values, but not really simplify it. So it's 64/3 minus 8 minus 24. Oops. Minus the quantity. So important, just, I know some people are like, oh, computational. I understand the concept. It's just the computation. One of the computational mistakes I see is just minusing out just the first term. So make sure you guys have quantity there. minus a third, minus a half, minus 6. And again, I get those values by evaluating at 1. So that is capital F of B minus capital F of A, where the capital F is your antiderivative. Okay, so all of that represents your net distance. And so net distance can be negative. If the area underneath the x-axis happens to be bigger than the area above the x-axis, you're going to get a negative value. Okay, it's kind of like overshooting your home. Okay, so it's like going 60 miles per hour, but then you go past your home. Your net distance is therefore negative. Okay, so total distance. Okay, so how do we do total distance? Total distance is a lot more involved. Okay, so I'm going to talk to you guys about how to do it if you were given this question without a calculator versus with a calculator. So let's talk without a calculator. Without a calculator, you guys would have to know roughly what the graph looks like. So let's say you were to like kind of get an idea of what the graph of t squared minus t minus 6 looks like. And you guys, no shame in this, but if you struggled on the free response because you couldn't factor a trinomial, can you guys, if you don't want to do it at a tutorial session with everyone too, feel free to set up one with me. That's something I want you guys to be able to feel comfortable asking me how to do. And it's fine. Every year I have kids in BC who still haven't figured out the way that they like to factor, so that, or either that or they just forget. So in this case for t squared minus t minus 6, that's basic enough that I can do guess and check on. So t minus 3, t plus 2. So that tells me that the x-intercepts are 3 and negative 2. So 1, 2, 3, negative 2. This is an upwards facing parabola, so I know the ends are going to go up. If it has to pass these 2 points, then roughly speaking, not paying any mind to where the vertex is, your parabola looks something like this. You don't need an exact picture of it. You really just need to know where it falls above the x-axis and where it falls below. Now, if I go back to the interval, they want me to find this total area or total distance from t equals 1 to t equals 4. So if I kind of just parse out that area, t equals 1 is here and t equals 4, let's go out one more here. T equals 4 is over here. Okay, so let me highlight the area that they're referring to. So when they say area, they actually mean the area between the x-axis and the curve. So do you guys see how I highlighted it? And from 1 to 3, we see that it's below the x-axis. So our net area for that is going to be negative, whereas above the x-axis from 1 to 4. And again, that is a distinction I want to make, or a point I want to drive in with you guys, is that when they're talking about area, they're talking about the area between x-axis and your curve. So if your curve is below the x-axis, you see my highlighted part is between the x-axis and the curve is below. If your curve is above the x-axis, it's between your x-axis is your bottom, and then your top is the curve. So the areas are highlighted as such. And then without a calculator, that would mean that I can't use my FN int. If I did, I can do something really quick and make it and calculate total distance. So here's my question to you guys. I know this is kind of a broad question, but how do you guys make something that is negative positive? What's one way to make something negative positive? Like force a negative number to be positive. Any ideas? Just arithmetic. Okay, we're all on the right track here. So many of you guys say, well, just multiply it by -1. So if I know this area right here is going to give me a negative number, but I want it to be positive, what I'm going to do is integrate like normal. Okay, I'm going to say from 1 to 3, I'm going to integrate t squared minus t minus 6, but realizing that that's going to give me a negative number, and I really want that to be positive. So what I'm going to do is multiply that integral, or that area, by a -1. So if this gives me a negative value, multiplying it by negative is then going to force it to be positive. Okay, and so that's the whole idea. If you guys watch my cursor here, if you guys were to force this part of it, take every single y value and put it above the x-axis, that's how we were talking about graphing speed as well. Then that way, if I just reflected it, that portion across the x-axis, that's what this is doing, then what it's going to allow me to do is force that area to then be positive. This part of it is fine, right? This part of it is above the x-axis. So I'm going to go ahead and integrate from 3 to 4 and not have to worry about the sign. So plus the integral from 3 to 4 of that same function. So t squared minus t minus 6 dt. And so I'm just setting up the integral for you guys. That's without a calculator. So kind of ask yourself, could I do this? I know it's tedious, but could I do this without a calculator? Sure, I would go about the process the same way, find the antiderivative, and then plug in these values, making sure to multiply this answer by a -1. Okay, so how would it change if you guys had a calculator? What a lot would change. Okay, so with a calculator, you technically don't need to graph anything. Okay, so with a calculator, no need to graph. And nobody actually typed it out in this class yet, but what is another way you guys can trick a negative number to becoming positive or forcing a negative number to be positive, besides by multiplying by -1? Okay, good. Yeah, so someone said absolute value. And yes, absolute value is the way to go on a calculator. So with a calculator, I wouldn't have to split any integral apart. I would say take the integral straight from 1 to 4. And when you type in your integrand, go ahead and take the absolute value of the whole thing. Okay, and the nice thing is like, well, why can't I do this without a calculator? Without a calculator, there is no derivative of, think of the antiderivative if you were trying to come up with this. There is no antiderivative of the absolute value function. So what we do is we can use our calculator, okay, and you guys can find the absolute value function under math, but under math, you guys would just type in fn int, type in math, find absolute value, put in the function, and then come up with the total distance. We'll have a little bit more practice with this, but I just wanted to kind of show you guys the difference between the two, what an integral really represents when you're integrating a rate of change. And so just, I know that the last class asked this question, I thought it was a good one, is that they were getting confused with all the terminology. So I just want to do just kind of a quick overview of what you guys have done so far. In this section right here, we were looking at the integral as the area underneath the curve, okay, between the x-axis and the curve. All of these fell above the x-axis. That's why they all ended up being positive. We saw that geometrically, this horizontal line, this semicircle, and this linear equation, we can find the area of it using geometry, you know, the area of a semicircle, the area of a triangle, or the area of a rectangle. But we also learned that many times we won't be able to do it geometrically because it's not a nice, perfect geometric shape. So the fundamental theorem of calculus allows me to take the antiderivative. So an antiderivative is the opposite of a derivative. If you guys have a function, you found the antiderivative, your antiderivative, if you were to take the derivative of an antiderivative, you would get back to your original function. So it's the opposite or the inverse of a derivative. Okay, so just notation-wise, little f is your integrand. If you found the antiderivative, that's the capital F. And then you would plug in your b, which is your upper limit of integration, and subtract out your a. And this is, again, finding your net area, the area between the curve and the x-axis. And this possibly could be negative. Okay, so the last thing we're going to go over for today is going to be, let me just make sure I'm good on time here. I think it's the perfect amount of time. So if you guys can find your trap rule notes, and we'll take the last bit of it on average value of a function on there. This won't take too long. So this is coming up with average value of a function. So we're going to start very similar to the trap rule, where we have just a function and, well, where did this formula come from? How did you come up with it? you guys, when you take AP Calc, it's not a proof-based class, which means that you don't do a ton of proofs. I remember all the math classes I took at UCLA, it was always proofs. Like, how did I get this theorem? And those proofs showed up on the test. So like proving mean value theorem, proving the average value of a function, all of those eventually appear on your test as a question. And that's what we call like theory-based calculus. And so I like to show you guys proofs here and there, just like it's basic, but it's important for you guys to be able to see where it comes from. Because a lot of people don't, I mean, me included, I just don't like to be given a formula sometimes and say, this is it. Like, where did it come from? Help me understand why it's true. So here's an example that you guys will not be asked to prove this on the test. It's just so you guys have an idea of what it's asking you guys to do. Okay, so let's say you had similar to trapezoidal rule. Let's say you have an interval a to b, and we'll list it off the same way where we have x values, let's say c sub 1, c sub 2, c sub 3, so on and so forth, all the way to b being c sub n. And so here's what the average value of a function is asking. Okay, so if the first x value is c sub 1, then that means that this y value is f of c sub 1, that this y value here is f of c sub 2, and so on and so forth, all the way up to this y value up above here being f of c sub n. So as you guys copy that down, let me ask you guys a question. If I asked you guys to find the average of something, what's the definition of finding the average of something? Like back to grade school. How would you guys find the average of a set of numbers? How would you guys find the average of a set of numbers? What do you guys do? Okay, so I'm reading out some sum of everything, divide by the number of values, finding the sum, divide by the amount of values, add and divide. Okay, you guys, so the average value of the function is really just asking you guys to find the average y value of the functions. So we're going to do that. We're going to take all of the values that you see there. And so here's the question I have for you guys. How many y values do you guys have between a and b? How many y values do you guys have between a and b? Okay, you guys have n number. And is that n number finite, or could it be infinite? Okay, good. Yeah, so some of you guys said there's an infinite number of y values. Technically, there's some y value between each one of these y values, right? There's an infinite number of them. So let's start off with, well, you guys told me just take the y values, the set of values, in which case this is the y values, sum them up all the way up to the nth term and divide it by the number of numbers. Okay, what expression represents the number of numbers? What would I divide by here? Yeah, so there's n number of numbers. So add up all the y values, divide by n. Many people look at that and, okay, that makes sense to me. Okay, the next part is, everything's always about, wrapping it up and making it look nicer. So what we're going to do is look at the 1 over n as just something that I can take, and it's a constant. So I'm going to move it outside of something called a Summa notation. And Summa was just to represent the sum. And so instead of writing this all out like, an infinite number of f of c sub n, what we're going to do is summarize that and say, okay, I have an infinite set of f of c sub n that I'm adding together, y values. And the number on the bottom, let's say I call this I. We usually call it I because that's called the index value. And so the index value here starts with whatever your first subscript is. So if your first subscript is 1, you guys are going to start with I equals 1. And we go up to however many we have in this, in which case the subscript ends at n. So if I equals 1 to n of f of c sub n. And the way that you guys would read the Summa notation is you would take the index, plug it into the n, and that should give you guys your first term. Summa represents sum. So then it would be take the next index up, which is plus 1. So f of c sub 2 should be next, f of c sub 3, all the way up to f of c sub n. Okay, so that was the notation. But again, this is where Leibniz stepped in, and he was like, that Summa notation is not very clear. Let's replace that Summa notation instead with an integral notation. Okay, and when we introduced the integral notation, he did a couple things to replace also some of the notation that we see here with the change of x. Okay, so when I go back to my picture, I recall that the change of x represented b minus a over n. Okay, and so here I see n, here I see 1 over n, and here I see n. Okay, in fact, do you guys see 1 over n also as right here, right? 1 over n right there. Okay, so what I'm going to do is I'm going to replace 1 over n with an expression that has b and a instead and change of x. So if I were to solve this expression for 1 over n, that would mean that I would multiply both sides by 1 over b minus a. Okay, so 1 over b minus a. Okay, so nicely, b minus a cancels out. On the left-hand side, I have change of x over b minus a. On the right-hand side, I have 1 over n. So here I have an expression for 1 over n, and here I have 1 over n is also equal to change of x over b minus a. So what I'm going to do is do a substitution here so that I have change of x over b minus a replacing 1 over n, and then I equals 1 to n of f of c sub n. Okay, well, our next move is to take this change of x and then move it to the end of that Summa notation. So I have 1 over b minus a, I equals 1 to n of f of c sub n times change of x. That should look really familiar to you guys. Sum up the y values, times it by a change of x. That's similar to Riemann sums, right? And so the next move is Leibniz move, which is replace the Summa notation with an integral. And in my integration, I'm integrating or summing up from the left endpoint of this to the right. So instead of the c sub 1 notation and the c sub n notation, I'm going to use a and b. So a to b. F of c sub n is the function f of x, sum up the y values. Change of x is the same thing as dx. And so this eventually becomes the average of all my y values. Also happens to be 1 over b minus a, the integral from a to b of f of x dx. Okay, so that is a formula you guys do have to know. You don't have to prove it. I just wanted to show you guys where it came from. And we'll do one example here. I think that's all we have time for. So example number 1, we're going to find the average value of y equals 1/2 x squared from 0 to 3. Okay, so let's write out the formula. The f average is 1 over b minus a. In this case, a is 0, b is 3. So if I put that into the formula, I have 1 over 3 minus 0, integral from 0 to 3 of what your function is. So 1/2 x squared, whatever you're trying to find the average of, dx. Okay, so we get 1/3. There's no need to use estimation for this. I can find the actual antiderivative here. A couple things you guys can do. If you're finding the antiderivative, there's already a 1/3 on the outside. You can also just take the 1/2 and factor it outside your integral and leave it as 1/2. And that way you're only integrating x squared. So 1/3 times 1/2 is 1/6. If I integrate x squared, I get x cubed over 3 from 0 to 3. Here's another option. Before you guys evaluate the definite integral, one thing you guys can also do is factor out the 1/3 as well, so you're not having to do all of that crunching of the numbers inside. So if you want, you guys can factor out the 1/3 to get 1/18 on the outside, and that way you're only plugging 0 to 3 into the x cubed part. So then we get 1/18 equals 27, 3 cubed. minus 0, right? Don't ever forget to plug in the a part. Then 27 over 18 is going to reduce to 3 over 2. And so if we take a step back of what this is saying if we add up the infinite number of y values between 0 and 3 of 1/2 x squared, then what we would get is that the average y value is 3/2. Okay, and I think I had the last class end with